What is?
Rainbows.
Yeah, they've come down a lot. All right, 12.2 is graphs and level curves. It's only going to take us a few minutes to talk about this. We're really just going to talk about domain, which we talked a little bit about at the end of class last time. Then we're going to jump to 12.3, which is limits and continuity. And then 12.4 is partial derivatives, which we have a card game for.
Oh, I remember the card game from last time.
Yes.
Is it like that?
Yes. Huh? Sorry.
Dang it, Adam. What? What's he dang it for? Because we know how you like to mess with the projector.
I think I did it. I turned it on, then didn't even see what the input was. So the first little bit here is just some terminology. So functions of two variables, what they mean when they say that are two independent variables. So technically in these types of functions, you're going to see three variables. But what they mean when they say functions of two variables is two independent variables. So these are like our surfaces. These would create surfaces in 3-space. So we could write them as z equals something with x's and y's, or f of xy equals a function of x and y. So back in algebra, when we first learn about functions, we name the function. We can name it f. We can really name it anything we want. When we first learn about functions, we use f just because it's the first letter of function. And then after the name, in the parentheses, we say what the independent variable is. So for functions of two variables, there are two independent variables. So we have x and y in the parentheses next to the name of the function. So we could either use z or we could use function notation.
She just said this morning that she needs new flip-flops.
Perfect.
Let me be sneaky and find out if she would want rainbows or something.
Z equals the natural log of xy, just another example. A function of two independent variables. We get to choose what we plug in for x and y, and then once we plug them in and do the calculation, it spits back a z value for us. So we could write it as z equals, or we could write it in function notation. And since there's two independent variables next to the function name, we indicate what the independent variables are in that function. So it says x comma y next to the function name. Is it confusing?
I just don't see why they just don't want to write the single. I missed what you said about the G one, but honestly, I didn't.
We don't always have to use f as the name of a function. Especially if we have a problem that has several functions in it, we don't want them to all have the same name. They need to have different names if they're different functions. So sometimes it'll be a z, sometimes it'll be function notation, but they mean the same thing. So these guys are surfaces in three-dimensional space because there are a total of 3 variables. The domain, if you think about what domain is back in algebra class, the domain is the set of all the values that we're allowed to plug into the function. Since these functions have 2 independent variables, we're actually picking 2 values to plug in. So the domain is going to be a set of ordered pairs. We have to pick an x value and a y value to plug in. So the domain's not a single set of number, it's actually 2 sets of numbers that go together. So we represent them as ordered pairs. So the domain is the set of all ordered pairs xy for which the function is defined. We only want to plug in numbers for the x and y that give us back a z value or a functional value.
I'll just read you what we did the other day.
Yeah, I just kind of rushed through that real quick in case anybody wanted to do some homework problems. And then the range. Do you remember what range is from just pre-calculus algebra?
Y values usually.
It's usually y values,
So
right?
Y is Z.
And right, y is the output in pre-calculus algebra. Here, our output is the z. So just to kind of be more general in case these variables change, the range is the set of all output values for the functions of 2 variables. When we know z is always going to be the output, it's going to be the set of z values. But it's just a single set. We only get a single number back when we plug in the 2 values for x and y. So it's just a single set of real numbers that we get back for f of xy or for z, depending on which format it's written in. So here x and y are the independent variables. And z is the dependent variable. Independent means you're allowed to choose them as long as they're going to give you back a value, as long as it's something valid that we're allowed to plug in to whatever operations are going on in that function, as long as they'll give us back an actual value for z. We don't get to pick the z values. The x and y and then whatever operations are going on determine the z values. So it's dependent upon the x and the y, and then the different operations we're going to apply to them. We're also going to see functions of 3 variables.
Functions of 3 input variables?
That's right. So that means 3 independent variables. So that terminology is telling us how many independent variables, not how many total variables we see, but how many independent variables.
Didn't you do an example in the last class?
We did an example really quick at the end with domain. And we'll do a couple more.
Which was one where you had, yeah.
Okay. I did one where it was like it was a rational function and it had like, I think it was x plus y in the bottom, and we had to write out the domain, and we wrote it in set builder notation, and we said y can't be negative x. Okay.
I remember my other notebook. The only one we did with that was equals 2x over x plus y. Everything else was the shades.
So these guys, with 3 independent variables, you're typically going to see x, y, and z as the independent variables. We need a 4th variable to represent the dependent variable, and you're usually going to see w as that 4th dependent variable. So we might see w equals x squared plus y squared plus z squared. It's got 4 variables in the equation, but it's 3 dependent variables.
How do you draw that?
We don't.
You draw it like my test script.
This would be drawn in 4-dimensional space. Inconceivable. So if we wanted to write this in function notation, we could say f of, what do you think is going to go in the parentheses? X, Y, Z. We have 3 independent variables. We need to list all of them. Equals x squared plus y squared plus z squared. W equals 2xy minus 3y times the sine of xz. Just another example of a function of 3 variables. On the right-hand side, we see x, y, and z all as independent variables. So we could write it as w equals, or we could write it in function notation. We'd give the function a name, and we would list all of our independent variables in parentheses next to the function.
We don't have to solve equation by 6.
No. We would take the derivatives, and we would do things with the derivatives, And those are called partial derivatives, because technically we can only apply our derivative rules to one variable at a time. So we're not really taking the derivative of the entire function. We're only taking the derivative of one of the variables, so it's called a partial derivative. And it's the same exact derivative rules that we learned in Calculus 1. You just have to be careful that you're only applying it to a single variable at a time. And that's what our card game is about today, partial derivatives. So these would be graphed in four-dimensional space, and we can debate for hours on what exactly that is, but we're not going to.
Show it. Would it be a three-dimensional enclosure?
But we're not going to. But we're not going to.
Would it just be like another line?
Yeah,
Z-axis.
but where's that line? How many legs does it take to get those sandwiches?
3. The owl says 3.
Huh?
The owl says 3.
Mike says a three. One.
3.
Two. A three. Maybe it's stupid. The world may never know.
So
So it's 4 dimensions.
four-dimensional space would take the sphere x squared plus y squared plus z squared and move it to different places and follow its path. Correct?
Pretty much. Essentially,
Yes.
like this.
Yeah, I was okay.
That's like, I was imagining on that 4-dimensional.
I'm like, stranger things, but it was like,
So this is a physics concept.
Like mathematics.
2-dimension.
Is this like a
It's like
quantum?
theoretical mathematics kind of.
Okay, so when I was in graduate school, I did abstract algebra, which this is not at all.
It's math.
But from the little bit of stuff I've watched on YouTube.
that's my reference.
What you're saying is you're next.
Yes, so what I'm saying is I'm an expert. The x squared plus y squared plus z squared equals a number is a sphere. So if we tried to graph this, what it's going to do is it's going to take all these different spheres and it's going to track them through space and connect them like in a tube. I don't know, kind of.
Is it a four-dimensional axis?
So it's like the shell.
I don't know. No, it's actually, it wouldn't be a tube. It wouldn't be a tube. It would be a growing sphere as W got bigger.
We can't think in 4D.
It would be a growing sphere. So starting off with W equals 0, this is just the point at the origin. W equals 1 is a sphere of radius 1. Okay, W equals 4 is a sphere of radius 2. W equals 9 is a sphere of radius 3. So it's tracking this sphere as it gets larger and larger and larger.
So it's like an infinitely big sphere with infinitely tiny spheres inside of it.
Yes.
Sphereception.
So 4 dimensions is not, the fourth dimension is not a solid object. The fourth dimension is tracking the change in the 3-dimensional object. It's tracking the change in the 3-dimensional object over time.
Time is our fourth dimension.
Not basically all equals.
Yes.
So it's like that cube.
What comes after 4 or 5?
Theoretical stuff. No, just made up shit. We're actually in multi.
Nothing I just said you need to know for this.
It's pretty interesting.
So technically these things would be graphed in 4 dimensions. because there's 4 variables.
But we have to represent them with 3D objects on a 2D page.
Yes. Exactly. The domain,
She's like, okay, let's stop.
It's like a cube of letters.
So what is the application for a 4D equation? Like, what's the point of somebody doing this if there's nothing?
for us right now, it's just practice with our rules.
Oh, really? That's it?
Just showing that the stuff that we're learning can be applied infinitely,
Oh, I got you.
so that someday if somebody does find a use for this, we know how to manipulate and do all this stuff with it.
Right now,
There are other people doing the research to find the applications for this.
It's like future proofing.
Mhm. Domain. If there are 3 independent variables, the domain is going to be a set of ordered triples. Mhm. And the range is exactly the same. If these are functions, you're only allowed to get one output. That's the definition of a function. You're only allowed to get one output. So the range is still just a set of real numbers. So the domain is a set of ordered triples. We've got to pick values for x, y, and z. But the range, there's only one output variable. So there's only one set of numbers for our range. X, y, and z are the independent variables. W is the dependent variable. And we're just going to do a couple quick examples of domain. We just did one at the end of class on Tuesday. So I just want to look at a couple more, and especially one that has 3 independent variables. And then we are moving on to section 3. Okay. We're still going to be using all of those same domain rules that we learned in pre-calculus algebra and trigonometry. We reviewed them a little bit when we started talking about domain of a vector valued function. And what I talked about at the end of class on Tuesday is what's going to be a little bit different here is because we've got two independent variables, we're not going to be able to solve for a set of x values and a set of y values individually. Usually what's going to happen is we're just going to be able to come up with a relationship between the x and y values that has to be satisfied. So in that case, we're going to write our domain in set builder notation and just list that rule that we can use all ordered pairs x and y as long as we follow this specific relationship between them. So we're going to use set builder notation to state restrictions on the domain. And the basic setup for our set builder notation is we start with a brace. And for our functions of two variables, we're going to say that we can use all ordered pairs x and y. The vertical line means such that, and then in this spot, we're going to list the restrictions. And then close your brace. So the domain is the set of all x, y, such that, and then we list out the restrictions that we have to make sure that we follow. Or if we're doing this for functions of three variables, we would say the domain is the set of all x, y, z, and then we list restrictions. So we're going to do a couple of examples. G of xy is equal to the natural log of the absolute value of x plus y. So what do we need to be careful of when working with natural logs? We can't take the natural log of a negative.
Zero? Yes, 0 is 1, right? Natural log of 0 is 1.
We cannot take the natural log of 0.
So y has to be greater than -8.
X plus y is greater than 0.
What do you see around the x plus y? Absolute values. So we've got absolute values around our x plus y. That fixes the negative part. That fixes the negative part, but it doesn't fix the 0 part. Okay? X plus y could still come out to be 0. So we still need to make sure that x plus y doesn't ever come out to be 0. And we need to solve it for one of them. Doesn't really matter which. Yeah, I like solving things for y. Good idea, Ethan. I agree. Y can't be negative x. If y is negative x, when we add them together inside, we're going to get a 0. So if y was 2 and x was negative 2, or if y is 5 and x is negative 5, or if y is 1/3 and x is negative 1/3. So it's an entire list of numbers that's not going to work.
What time do we start?
What time of,
Did y'all start?
we have classes from 1 to 3:30.
And what time will you get to work?
Usually any minute now.
Okay, let me know. I'll
Okay.
be in 71 now.
Okay.
How y'all doing?
Great.
That's how we started. I thought you were getting a job. I was like, ooh.
I said classes from 1 to 3:30. I was trying to figure out where she was going with that.
I was like, oh, she knows. She got microphones in here.
She plugged her.
Think about that
I hope not.
sometimes.
I hope not. That's a-
Y can't equal negative x. That's the restriction. We have to make sure that our x and y's follow. Okay?
Are you scared now?
No,
When you called her a room, you get scared?
no, it's engineering stuff.
I just not. Maybe you heard what I read on Snapchat. I was reading off Snapchat.
No. Y can't be negative x. So we don't want to just say y can't be 5, x can't be negative 5. There are an infinite number of possibilities that go together for the y and the negative x. Okay? So we just have to make sure that we follow that restriction. So we write it in set Builder notation. So the domain for this function, whose name is g, so we write a little subscript g, capital D subscript g, the domain of g, is the set of all ordered pairs x, y, such that, and we list the restriction that we have to follow. So we'll get an answer back for the output as long as y does not equal negative x. As long as we avoid those, we're good. Yeah, not too bad. You just have to remember all that stuff from algebra about these functions. You have to remember that log, we can't do negative or 0. So it's really all that algebra stuff that we need to be careful about. Did I call that A? I did. Good. We're going to give a set Builder notation, but we're going to do a verbal description as well. So f of x, y, z is the square root of x squared plus y squared plus z squared minus 9. So what do we need to be careful of with square roots? The stuff inside can't be negative. So how can we write that algebraically? We can't because the pluses and minuses. Because the pluses and minuses, we can't. Instead of saying, instead of using a less than symbol and then putting a don't do this, there's something else we can use instead. Greater than or equal to. So the opposite of less than is greater than or equal to. So we're going to say that x squared plus y squared plus z squared minus 9 must be greater than or equal to 0. When we're doing square roots, we need to make sure our radicand, which is the stuff under the square root, is greater than or equal to 0. We can do the square root of 0. It's equal to 0. And then we can do the square root of anything positive.
It just seems so obvious.
What?
Is that the answer?
No.
I was gonna say.
Well, it could be, yeah, but I'm gonna move the 9 over.
Okay, yeah.
So x squared plus y squared plus z squared must be greater than or equal to 9. So we're going to write that in set builder notation. The domain for, what do we call this guy? F? What in the world? The domain for F,
X, Y, Z.
x, y, z, right. This has got 3 independent variables. It's the set of all x, y, z such that
X plus what?
x squared plus y squared plus z squared must be greater than or equal to 9.
There's more than one restriction you set there about this.
Just a comma. Just a comma is fine if there's more than one restriction. Or you can just say and. We're going to give a verbal description of that, and then we're going to go on break. So we can use all the points for which x squared plus y squared plus z squared is greater than or equal to 9. X squared plus y squared plus z squared equals 9 is a surface in space that we have talked about before. What is it? It's a sphere. Give me one more detail about it.
Radius 3.
A sphere of radius 3. So x squared plus y squared plus z squared equals 9 as a sphere of radius 3. What does the greater than symbol mean?
Yeah.
We're not going to change the size of the sphere. It means we can use all the points. The equals means we can use all the points on the sphere. And the greater than means we can use all the points outside of the sphere. So at the beginning, Joa said we can't be less than. That means we cannot use the points inside the sphere. But we can use the points on the sphere, and we can use the points outside the sphere. Okay? So we can use all points on or outside of the sphere centered at the origin with radius 3. So the equals means it's on the sphere, and then the greater than means outside the sphere.
You put E on the outside.
No.
I see it.
So we can use all points on or outside the sphere centered at the origin of radius 3.
Yeah, she could have been serious. She didn't have to fix it.
I am making an executive decision to not talk about level curves at this moment because we need to talk about limits and keep on a trucking. We probably will come back to level curves later when we talk about gradient.
Puts me in mind on the oversized orange.
You talk about fruit. I don't know. Fruit in 3 dimensions.
Oh.
Most of the limits are pretty easy, and you can do them by direct substitution. Did you get a bad one?
No,
I told you those are sketchy.
I don't.
Oh.
I don't taste anything. Oh, strawberry.
So we're always going to try direct substitution first. And that's the same strategy we use in Calculus 1. Always just try to plug your values in first and see if you get an answer. So if we're asked for the limit, since we have two independent variables, they have to give us values for both of them. We've got to replace both of them. So they're going to say as x, y approaches, and they've got to give us values for both, since it's a function of two variables. Always just try direct substitution first and see if you can get an answer. So as xy approaches to -1, we want to know where the function 2xy over y plus x looks like it's going to. So we just plug in 2 for x and -1 for y and see if we can get an answer. In the top, we got 2 times 2 times -1. In the bottom, we've got -1 plus 2. So that's -4 over 1, which is -4.
The regular ones.
Did you even try the bottom machine?
No, it doesn't work. I don't know. I'm guessing it's supposed to. Doesn't that machine have to take orders? Yeah, I did. I used that one, but they only have the green ones.
The actual, is it like, yeah.
Just original.
There's fruit punch ones or off?
The red bag? I've never tried those first. Oh yeah, I think I have tried those.
Every single one is just the same, but it's all.
The limit as xy approaches 0, 3 for 2xy over xy minus 2x. Always try direct substitution first and see what happens. Yeah. Zero over 0, which is indeterminate. 0 over 0 is indeterminate.
Just factor it up.
L'Hopital's, we do not have a L'Hopital's rule for functions of several variables. But this one, there is a common factor, correct? There is no L'Hopital's.
So there's a hole there. I still don't know what L'Hopital's. Oh yeah, I do remember.
That's where you take the derivative of each piece and try and plug in again. Try again.
Take a derivative of each piece.
You don't have to do quotient rule. You just take the derivative of the top, take the derivative of the bottom, and then do direct substitution again.
What situation is that for?
indeterminate
I
forms.
know, like.
0 over
any
0 or infinity over
just something
infinity.
you can try.
Mhm.
Oh, never mind.
So there is no L'Hopital's rule for functions of several variables, but on this one, there is some algebra that we can do to fix it. One of the cases that leads to 0 over 0 is a common factor. And we do have a common factor of x here. So we can pull out an x and cancel it away. Yep.
We can do the X. Wow.
So we factor out of x, and then we have a common factor of x in the top and the bottom. And when we pull it out and cancel, we're left with 2y over y minus 2. And now we can try to plug in again. We only have y's left. And what did they say our y value is approaching?
3.
It's approaching 3. Yep. So this is 2 times 3 over 3 minus 2, which is 6.
There would be a hole there.
There is a hole, yep. When you can factor and cancel, it creates a hole in the graph. So what we did here is we checked for an algebra solution to the indeterminate form. Zero over 0 sometimes, not all the time, but 0 over 0 sometimes means that there's a common factor. Is that the right there? It's a location.
There it is, yes.
Okay. In Calculus 1, to show that a limit exists, we had to show that the left-hand limit and the right-hand limit were doing the exact same thing. Okay? So if this is the graph for f of x, we had to show that the limit as x approaches a from the left and the limit as x approaches a from the right for f of x were equal. If they were different, that means there was a gap in the graph. That means on the left we're approaching one value, but on the right we're approaching something completely different, and there is this big old gap. And if there's a gap, that means the limit does not exist. Okay? And that's because on the x-axis is just a number line. It's one-dimensional. So all it has is a left and a right. When we jump to three-dimensional space, and our domain now is a set of ordered pairs, we're working with the entire plane. And there's not just a left and a right anymore. If we get, in order to prove that a limit either exists or does not exist, does not exist, we can't just show that it comes from the left and the right to the same spot in the plane. In the plane, it can come from an infinite number of directions. And this is really hard to draw. But if I wanted to approach the origin, I can come in that direction. Let me change the color. Those are all straight lines too. We don't have to come in on a straight line. I can come in on a parabola. These are all flat on the XY plane. All of those red arrows are flat on the XY plane, trying to approach 0, 0. We have to show that if our limit exists, that all of those directions, that the limit is approaching the same value. That would be impossible because there are an infinite number of paths that approach 0, 0. So really what this is more useful for is a proof by contradiction. We can prove that the limit does not exist if we can find a path that the limit comes out different. If any one path gives a different answer, that means along that one path, there's a gap. So the limit doesn't exist. So our plane consists of an infinite number of paths that can approach a single point. And the limit on every single one of them has to be the same if we want the limit to exist. But because there's so many, it's really going to be impossible for us to do. So really, what this is going to be more useful for is for us to show that it does not exist by finding a path where the answer differs. We're going to prove that this limit does not exist. X squared y, the limit as xy approaches 0, 0 for x squared y over x to the fourth plus 4y squared. What do we get if we try direct substitution? We get 0 over 0, which is indeterminate. They could have a common factor, but look at your denominator.
Since we're just using 0 anyway, since it's 0, 0, we know it's always going to be 4.
There's a factor in everything. The denominator is a sum of squares, and our two terms don't have anything in common. So there's not going to be anything we can do factoring wise in our denominator. So we're not going to be able to fix this with algebra.
Is this the one with the pad?
Yes, this is the
Always
one.
one.
Mhm. We're going to show this by approaching 0, 0 along different paths and showing that we get different answers along different paths. So we cannot fix this one with algebra. So we're going to pick a path in the xy plane that goes through the point 0, 0. And by path, I just mean an equation.
Y was X.
Y equals x goes through the point 0, 0.
Oh, so we replace X, then the Y.
You could either replace all the y's with x's or you could replace all the x's with y's. It's up to you.
You know the company Cisco?
Yeah.
Did you know the CEO of that went to Rockingham High School?
Mm-mm. So we replaced all the y's with x. And now it's just a limit with one variable. It only has x. So when the limit as x approaches 0, it's still 0 over 0, but now we can do algebra. What kind of algebra can I do in the denominator? We're going to pull out an x squared. And then we can cancel x squared in the bottom with 2 of my x's in the top. And now it's the limit as x approaches 0 for x over x squared plus 4. And this is not indeterminate anymore. Direct substitution gives me 0 over 4, which is 0. So along this path, along the y equals x path, it's approaching 0. Now we need to find another path where we get a different answer. And we're almost done.
So find a path where you get another answer.
We need another graph in the xy plane that goes through 0, 0.
5 is x squared.
Sure. Y equals x squared. Also goes through the point 0, 0. So that means we're going to replace all the y's with x squareds. So go back to your original. Replace all the y's with x squareds. So in the top, we have x squared times x squared. In the bottom, we have, oops, I made a mistake. In the bottom, we have x to the 4th plus 4 times x squared squared. So all I've done is I've replaced my y's with x squareds. So this is x to the 4th in the top, x to the 4th plus 4x to the 4th in the bottom, which is really 5x to the 4th. And those x to the 4ths can cancel. What's this limit? 1/5. We found a different path that gives a different answer. That means at 0, 0, there is a gap in this graph, which means the limit does not exist.
So for these, we pretty much have to guess until we can find the function, right?
Well, there is a trick. Usually we want to be able to combine these terms so that we can do the algebra to simplify it. So in the bottom, if I want my x to the 4th and my 4x squared to eventually be able to combine, that's not what the right thing I'm looking at. If I want to be able to combine these two terms, then I need my y squared to turn into an x to the 4th. So to make them combine, I need my squared to turn into a 4th. So I need to plug in a squared there. If you square a square, it turns into a 4th. So there is some kind of thinking ahead with your algebra to figure out what's going to work and what's not going to work. Usually, you can always do y equals x and get a baseline. And then you need to do a little bit of thinking ahead with your algebra of, if I want those terms to combine, what do I need to do? If I need my squared to turn into a 4th, then I need to square a square, so I need to use the square function. All right, we're going to do one more real fast, then we're leaving. This one also does not exist. Algebra will not fix it. Direct substitution is indeterminate form. We're just going to jump right into our paths. You need to make sure that your path goes through the point that you're doing the limit for. So we need to make sure that we pick a path that goes through 0, 0. So somebody give me a path that goes through 0, 0. Y equals x. So I'm going to replace all of my y's with x's. And what do we get for our limit? But it simplifies. Now that it's all x's, we can do some algebra there. We have 2x squared over 2x squared. So we get 1. So now we need to make sure we don't get 1 next. So we check another path. If we do get 1 again, then we just have to do a third one, or a fourth one, or a fifth one. Y equals x to the 4th. Okay. So we're going to replace all the y's with x to the 4th. So I'm going to go back to my original. Let's see what happens. So 2x times x to the 4th over x squared plus x to the 4th squared. So that's 2x to the 5th over x squared plus x to the 8th. And direct substitution 0 over 0, but we can do some algebra simplifying now. We're going to pull x squared out of the bottom. And we can cancel it with 2 of them in the top. So now we've got the limit as x approaches 0 for 2x cubed over 1 plus x to the 6th. And we get 0 over 1, which is 0. 2 different paths approaching the same point, and we got 2 different answers. That means at 0, 0, there is a gap in the graph. That means the limit does not exist there.
If we're doing one of these and if we get the same number, is it probably because we don't need to be doing that?
You technically can't prove that a limit does exist this way. You probably haven't found the right path. But Tyler said there's only probably 2 path questions. And I think they even give you the path. They just want you to figure out the limit.
I think it's like multiple choice.
Okay.
It gives like several options,
Mm-hmm.
and then you have to figure out.
Usually if the limit does exist, you'll be able to simplify it with algebra. There are also some instances where we can change it to polar coordinates, and it will simplify nicely with polar coordinates. In the interest of time, we're moving on though. We still have a lot to do. But we're out of time for today. So that's most of section 2.3. We didn't talk about continuity. Continuity, though, is kind of like the domains and the limits combined. If we combine the concept of the domain, the numbers that we're allowed to plug into a function, and also all the places where the limit exists, that builds up our list of places where a function is continuous. So again, we didn't get to our card game, but yes, I have a card game for partial derivatives. It's not.
Derivatives first.
I know. That's 12.4.
It's the end of 12.3.